Welcome to Free Learning Academy. Let's simplify first come, first serve scheduling algorithm. What if I told you that sometimes the simplest way to schedule tasks in a computer is also the most unfair one? That's exactly where first come, first serve comes in. Just like a queue at a ticket counter, whoever arrives first gets served first. No questions asked. Now, in the context of an operating system, we already know that multiple processes are waiting in the ready queue, all competing for CPU time. The job of the scheduler, which we briefly touched earlier in CPU scheduling basics, is to decide which process gets the CPU next. First come, first serve is one of the simplest strategies to make that decision. Here, the rule is very straightforward. The process that enters the ready queue first will be executed first. Once it starts running, it will continue until it finishes. There is no interruption. This makes first come, first serve a non preemptive scheduling algorithm. If you remember the idea of preemptive versus non preemptive scheduling, this means once a process gets the CPU, it cannot be taken away until it completes its execution. Let's understand this with a simple example. Imagine three processes arriving in the system. Process P1 arrives first, then P2, and then P3. To make math simple, let's assume they all arrived at time zero. They're burst times, which means the total time they need on the CPU are different. Let's say P1 needs 5 units of time, P2 needs 3 units, and P3 needs 2 units. Now, according to first come, first serve, the order of execution will strictly follow arrival order. So P1 will run first for 5 units. After that, P2 will run for 3 units. And finally, P3 will run for 2 units. To visualize this better, we use something called a Gantt chart. Think of it like a timeline that shows which process is running at what time. So in our example, from time 0 to 5, P1 is running. From 5 to 8, P2 runs. And from 8 to 10, P3 runs. This simple timeline gives us a clear picture of execution order. Now let's go a bit deeper and calculate some important metrics. We already discussed scheduling criteria earlier, like waiting time and turnaround time. Now we actually apply them. Waiting time is the amount of time a process spends waiting in the ready queue before it gets CPU access. Turnaround time is the total time from arrival to completion. For P1, since it starts immediately at time 0, its waiting time is 0. Its turnaround time is 5 because it finishes at time 5. For P2, it has to wait until P1 finishes. So its waiting time is 5. It starts at 5 and finishes at 8. So its turnaround time is 8 minus its arrival time. For P3, it waits for both P1 and P2. So its waiting time is 8. It finishes at 10, so its turnaround time is 10. If you look closely, you'll notice something interesting. Even though P3 only needed 2 units of CPU time, it had to wait for a long time just because it arrived later. This is one of the biggest drawbacks of first come, first serve. Now, let's take a slightly more realistic example where processes do not arrive at the same time. And this changes how the scheduling works. Imagine three processes again, but this time P1 arrives at time 0, P2 arrives at time 2, and P3 arrives at time 4. Their burst times are P1 equals 5 units, P2 equals 3 units, and P3 equals 2 units. Since first come, first serve follows arrival order, P1 will still execute first because it is the only process available at time 0. So P1 runs from time 0 to 5. Now, during this time, P2 arrives at time 2 and P3 arrives at time 4. But they have to wait because P1 is already running and first come, first serve does not interrupt. Once P1 finishes at time 5, the next process in the queue is P2, which arrived earlier than P3. So P2 runs from time 5 to 8. After that, P3 gets its turn and runs from time 8 to 10. Now let's calculate the waiting time. For P1, waiting time is 0 because it starts immediately. For P2, even though it arrived at time 2, it starts at time 5, so its waiting time is 5 minus 2, which is 3 units. For P3, it arrives at time 4 but starts at time 8, So its waiting time is 8 minus 4, which is 4 units. Now let's calculate turnaround time. Turnaround time is completion time minus arrival time. For P1, it completes at time 5 and arrived at 0, so turnaround time is 5. For P2, it completes at time 8 and arrived at time 2, so turnaround time is 6. For P3, it completes at time 10 and arrived at time 4, so turnaround time is also 6. This example clearly shows how arrival time affects waiting and turnaround time, even though the execution order still strictly follows who came first. Let's take another example to make this even clearer. Suppose a very long process arrives first. Say it needs 20 units of time. After that, several small processes arrive, each needing just 2 or 3 units. In first come, first serve, the long process will occupy the CPU completely and all the smaller processes will be stuck waiting. This situation is often called the convoy effect. Imagine a slow truck on a narrow road and many fast cars stuck behind it. Even though the cars can move faster, they cannot overtake. Similarly, in first come, first serve, short processes get delayed because of one long process ahead of them. Now, from a system performance perspective, this is not very efficient. Short jobs that could finish quickly are forced to wait, increasing average waiting time. But despite this drawback, first come, first serve has some advantages. First, it is extremely simple to implement. There is no need for complex logic. The operating system just maintains a queue and executes processes in order. Second, it is fair in a basic sense. Every process gets its turn in the order it arrives. There is no starvation, meaning no process is ignored forever. Eventually, every process will get CPU time. This makes first come, first serve useful in certain situations where fairness and simplicity are more important than performance. For example, in batch systems where jobs are processed without user interaction, first come, first serve can work reasonably well. However, in interactive systems like the ones we use daily, first come, first serve is not ideal. Imagine clicking an app and waiting because some heavy background task is running first. That would lead to poor user experience. Now, one more thing to understand is how first come, first serve connects with other scheduling algorithms. First come, first serve is often considered the baseline. More advanced algorithms like shortest job first or round robin try to improve upon its limitations. For example, shortest job first tries to solve the convoy effect by giving priority to shorter jobs. Round robin introduces time slicing so that no process holds the CPU for too long. You will see these improvements clearly in the upcoming topics. So, in a way, first come, first serve helps us understand the problems that more advanced algorithms are trying to fix. To summarize the idea in a simple way, first come, first serve works like a queue. The first process that arrives gets the CPU first and runs until completion. It is simple, predictable, and fair in terms of order, but it can lead to long waiting times, especially when long processes come first. And that's the key takeaway. Sometimes being fair in order does not mean being efficient in performance. That balance between fairness and efficiency is what makes CPU scheduling such an interesting topic. That is it for this video. See you in the next one.